Our topic of discussion today is independence of random variables. In the last lecture, we saw different notions of independence. Two events, A and B, were called independent. We defined the definition to be probability of A intersection B is equal to PA multiplied by PB. This notion can be generalized. We can talk about independence of a family of events. In this case, there was no single definition of independence. We saw that there were two different definitions: pairwise independence. In this case, probability of AI intersection AJ was P of AI multiplied by P of AJ for all elements in the family. So any two elements of this family were independent. A stronger notion was mutual independence. It said that if we pick any subset of I, the probability of this intersection is multiplication over individual probabilities. This held for all subsets of I. We also noticed that mutual independence is a strictly stronger criteria. There can be families which are mutually independent but not pairwise independent. We will extend all these criteria to random variables. So if you remember, when we talk about random variables, it's intuitive to think about these kind of events, right? So when the random variable actually takes value x, then even we can talk about the random variable restricted to some event b. In this case, probability that my random variable restricted to some event b is equal to x is probability of x equal to x. So I'm giving my random variable as a collection of these kind of events. This gives us the definition of two random variables being independent. X and y are independent if probability that x equal to x and y is equal to y is probability x is equal to x, probability y is equal to y. And this should hold for all possible elements in the range of x. We said that two events are independent if this condition held true for these two events. Now, when you want to define independence for two random variables, we say that all possible events related to x and y. So, when I say events related to x, I talk about these events. So, all such events are independent. Then we say that random variables x and y are independent. Similarly, this can be extended even to a family of random variables. So suppose now I have a family of random variables and we talk about whether they are independent or not. Again, I will have two conditions, pairwise, which will mean that for any pair, I will have independence condition. So this is probability xj is equal to xj, and this should hold true for all I comma j xi xj. And in the case of mutual, again, this will hold true for all possible subsets. So I look at the events, j is equal to xj, and this is the product of the corresponding probabilities. And this will hold true for all subsets of I. They are not elements, they are subsets of I, and all possible choices of x1, x2, which are in the range of xj. And like the case of events, mutual independence is stronger than pairwise independence. That means mutual independence implies this is not. As an exercise, you can find an example of random variables which are pairwise independent but not mutually independent. You might be wondering, why have we defined such complicated concepts? So let's take an example of application of this concept in computer science. This is called hashing. You might have seen hashing before. The major application given for hashing is that you want to store a stream of data such that each data element comes from a big range, say S, such that this is pretty big. And now you can see that to store every element, I need these many bits. And then if the S is pretty big and my stream is very big, then I need lot of memory or lot of. So the way to compress this thing is to actually map the elements of S to some small set such that kernelity of T is much smaller than S. And then instead of storing elements of S, we store elements of T. This will happen if the number of collisions under this mapping are small. You actually want to have a randomized hashing. So in this case, the mapping from S to T is some function phi r, where r is picked randomly from some set r, and then we even want that for all elements which we are encoding, the image under hashing is uniformly distributed. So let me define this very formally. Given three sets R, S, and T of hashing from S to T under R is a collection of functions. What are the functions from? The functions are from S to T, and every function I will denote it by phi r. So R comes from capital. So this is called a hashing, and notice that these elements can be thought of as a random variable. In the general case, R is picked uniformly from R. Take some time to make sure that you understand all these concepts. You have three sets, you want to map from S to T, but this map is random. So for every key, I have a different function. And what do we need? We need that phi rs is distributed uniformly. Under every random key R, I'm just going to the same element in T. Then there is no use of using all these random keys. And the other thing is that we, in some sense, we want collision to be minimized or being small. We will take care of this by saying that the knowledge of phi rs should not give any information about the other random variable phi r s prime. So this should remind you of pairwise independence, and this gives us the way to model our constraints in terms of pairwise independence. This is the use of pairwise independence. We will say that hashing is pairwise independent if and only if two conditions are satisfied. First is that phi rs are uniformly distributed. This is the condition which was there before. And the second condition, that the number of collisions should be small, or knowing phi rs should not tell us anything about phi rs prime. We will encode this as saying that this family of random variables, notice that there is a random variable for every small s element of capital S. This family is, in the exercise, you will show that these two conditions are exactly equivalent to probability that phi rs is equal to t intersection phi rs. So if you pick two general elements, so phi rs is equal to t should be uniformly distributed 1 by t, phi r of s prime is equal to t prime, and this should come out to be 1 by cardinality of t square. This should hold for all s prime element of s. Again, s should not be equal to s prime, otherwise this can't happen. And for every t prime element of t. So we got a very nice notion of hashing using our concept of pairwise independence. So let me just say why it is nice. We got this definition, that probability of phi rs is equal to t. So if I pick two different elements, s and s prime, they map to some t and t prime almost uniformly. And this holds true for all s prime t prime. And what is this condition implying? This condition implies multiple things. First is knowledge of phi rs does not reveal phi rs prime. Right? And the other thing is, this will also imply that number of collisions are small. That is just obtained by setting t is equal to t prime, and you see that the probability of collision is very small. And this also implies that phi rs is uniformly distributed. So all these things we can nicely capture using the notion of pairwise independence. If you are not convinced yet, let me just give you an application of pairwise independence hashing. How can this be useful? So let's take this problem where Raj and Simran wants to communicate. We will say that Raj wants to communicate some message to Simran. The problem is, message will go through Amrish. Unfortunately, I don't remember the name of Amrish Pudding, DDRJ, so just call him Amrish. So the message has to go to Simran, but through Amrish, though Simran is worried that the message can be tempered. And the age-old problem is, how does Simran know that the message is from Raj and not Amish? We will solve this assuming two assumptions. Raj and Simran share a secret key, which obviously Amish doesn't know, and Simran is ready to accept small probability of error. At this point, you can pause, you know pairwise independent hashing, and try to construct a scheme to achieve this feat. So we want to make sure that Raj is able to communicate message to Simran coming from some set capital S. someone should be able to say with high probability that the message is from Raj and not from Simran. So try it out, pause the video and see if you can do it. The answer is not very difficult. So as I said, we will assume that Raj sends a message from some set and Raj and Simran share a secret key which is going to be our element of R. We have at our disposal a hashing scheme. If you remember, the protocol is very simple. Using this random string R, Raj sends S, Ramesh sees this message. He can probably tamper with this message, but then the point is that Simran can just check if he receives X comma Y, then is fire of X equal to Y. If this condition happens, so Simran receives X comma Y, if fire X is equal to Y, she accepts the message that it comes from Raj, otherwise if this condition is not true, then she rejects. And we want to show that with high probability the message actually came from Raj and not Amrish. If you think about it, the intuition is pretty straightforward. When Amrish sees X comma Y, he sees a message which satisfies this condition. And now he wants to construct an X prime comma Y prime such that phi r X prime is equal to Y prime and X is not equal to X prime. Because if X is equal to X prime, then he is not able to cheat system. So this is what needs to happen. But intuitively, when Amrish sees XY, he has no clue about the random string R. He cannot distinguish whether it came from R or R prime. That is what the pairwise independent chain gives us. Once he does not know R, there is no way to construct X and Y prime, X prime and Y prime, such that this condition happens. We will see this. Define the event E to be Amrish is able to cheat. We want to bound the probability of E. This I will do by dividing it into small intervals, which are that X, the message given by Raj is S intersection the message which is sent, the hash is T intersection with T. So you will notice that this is just dividing my entire sample space into cardinality of S, cardinality of T disjoint events. So this is very simple partition bound, and now I will just bound this quantity. This becomes under some random variable S, this is T, and then E means that Amrish is able to find some X prime and Y prime, so that phi X is equal to Y prime and X prime is not equal to S. Now if you notice that these three events are independent of XP because these have nothing to do with Raj picking a message. So this becomes probability of X is equal to S, probability phi S is equal to T intersection phi X prime Y prime intersection X is equal to S. And this quantity usually, this comes from the fact that things are pairwise independent. So this is equal to probability x is equal to s 1 by probability of t square. We can still simplify it more. This is the quantity which I want to simplify. Now probability of x equal to x does not depend on this summation. So this becomes probability x is equal to s summation t element of t. Again, this will become 1 by t. And now this quantity is just 1. So we get that Simran is food with probability bounded by 1 by t. So using this pairwise hashing, Raj and Simran can communicate and the error probability is only 1 by t. So we can use this pairwise independence.